فسرت من هناك احسن. كده مش ريسبوند خالص. لا خليني من هناك احسن. Welcome everybody. Now we have. I want to check that everybody can hear me. Is it okay? Can you hear me?
Yes, Doctor.
Okay. Yes, okay. Welcome everybody to our next lecture today. The next lecture today is about earthquake damage mitigation of Sahara Pyramid through vibrating barriers, a numerical study by Mohanad and Ashraf Ayub. They are our partners in this project, and they did a great job on modeling, numerical modeling of the Zoser pyramid. And you will see a nice lecture now. It will be followed up by another lecture on Cairo Citadel. Okay, so I will leave Mohanad, I think, to share his screen and start his presentation. Go ahead.
Thank you. Thank you. Hello, and thank you for having me today. I am Dr. Mohanad Alfach from the team of Professor Ashraf Ayub at the City University of London. We are part of universities work in this project with the Cairo University and the University of Brighton with the fund from HRC. I am going today to give a short presentation about our numerical study. This presentation will be on earthquake damage mitigation of Saqqara Pyramid through vibrating barriers. A numerical study work focused on the inelastic behavior of the pyramid and the soil, and then the efficiency of the using vibrating barrier. As the idea of vibrating barrier based mainly on the exploiting the beneficial effects or impacts of soil structure interaction mechanisms. So I would like to start with one of the most important factors which control the soil structure interaction, which is the interaction between the fundamental frequencies. In our case here, we have carried out the analysis, numerical analysis, under 12 seismic records recorded in Egypt. The fundamental frequencies for these records ranges from 0.14 to 7 hertz. The fundamental frequency or natural frequency of the soil, which is here limestone, it is 22.40 hertz. The fundamental frequency of the pyramid is 0.52. As you can see here, some of the records have fundamental frequency close from the fundamental frequency of the pyramid. In our numerical model, the numerical modeling process has carried out using the finite element software Abacus 2019. The numerical analysis performed in 4 steps. First step, the elastic behavior of the pyramid without soil, then the elastic behavior for the system, soil structure, soil and the pyramid. Then we have analyzed the plastic behavior of soil and pyramid. And finally, we have added the vibrating barrier to study the effect or the impacts of using this vibrating barrier. Firstly, we have here the same material for the pyramid and the soil, which is limestone. Here we have the elastic properties for this material, which is 45 gigapascal, Poisson ratio 0.25 and density 2000. Also, we have used the concrete damaged plasticity model for simulating the elastic behavior for the pyramid and the soil. Here we have the data used for simulating the uniaxial compression stress behavior in concrete damaged plasticity model. We have used sigma C maximum equal 10 megapascal and tensile stress equal 1 megapascal, 10% of sigma C. Here we have our model. The mesh, we have the dimension of the soil, as you can see here. The length of the soil used in this analysis, it's 500 meter, and the depth of the soil 35 meter with width 300 meter. Considering the high sensitivity of soil structure interaction, we have taken some arrangement. For example, we have used free-filled or quiet boundaries here at the boundaries to avoid the reflection of seismic wave on the structure. Also, because this kind of analysis, it is very costly in terms of processing capacity and time. So we have used the density for the mesh decreased when we go away from the structure to minimize the processing capacity time for this kind of analysis. Here we have the same model, but here we have added 2 vibrating barriers. Here we have the vibrating barrier range. We have the dimension, it is 40 meter, 250 meter, and with depth 35 meter. From concrete, we have 2 here, 1 and here 1 vibrating barrier in the finally in the 4th stage of this study. Here we have the Fourier analysis, the seismic records recorded in Egypt recently. As you can see here, we have the frequency from 0.14 to 2 with amplitude centimeter second square. Also, here we have the Fourier analysis for Aqaba record. We have records for Aqaba. We have Aqaba east-west and Aqaba north-south. As you can see here, we have frequencies or fundamental frequencies till 7, but here we have the maximum. It's about 2.3. So on first step, we have run the numerical analysis under the record of Aqaba east-west. Here we have the record acceleration time history with time. The duration of this record, it's 40 seconds with maximum acceleration equal 0.09, which is relatively weak acceleration. Here I have for this record. As you can see, the fundamental frequency of Aqaba is 2.3, which is a little bit far from the fundamental frequency, which is 0.52. Here I have the results. I have the acceleration for plastic pyramid and soil, plastic behavior for the pyramid and the soil. And in case they're using plastic pyramid for pyramid and soil and using vibrating barriers. As you can see here, I have the acceleration or the envelope, of course, the maximum envelope without using the vibrating barrier. I have something like 1.3. Here, after using vibrating barrier, I have huge reduction in acceleration. It is up to 80% reduction in acceleration at the pyramid with the using a vibrating barrier. I have to mention here the mass of the vibrating. It is equal the mass of the pyramid. It is the first analysis. So we have used the big mass equal the mass of the pyramid. So we have here huge reduction, about 80% in acceleration. In terms of displacement, also here I have without vibrating barrier. Here with vibrating barrier, it is not exactly linear, but with the scale, there is some differences, but with the scale, it is not very clear here. But actually, we have also big in displacement, up to 90% with the using vibrating barrier. Here we have for the stress or vertical stress according to von Mises. We have without the using of vibrating barrier and with using vibrating barrier. We can see here we have some tension, but it is very small, 0.6. And here we have more, but here in the pyramid, we don't have this tension. We have reduction in compression stress in the pyramid when we have used the vibrating barrier up to 94%, 85%. So it was a huge reduction in compression stress in the pyramid. We have here actively built the filler zone in the pyramid without vibrating barrier. I have large part of the pyramid has already plasticity and filled. Here with the using vibrating barrier, I don't have anything. It is 0. Here I have 1 for the red zone. So large part of the pyramid has already in the filler or plasticity. Also, I have here equivalent strain which the materials in elastic deformation without using the vibrating barrier. So we have value -3. It is small, but when we have used the vibrating barrier, the equivalent plastic strain reduced about 94%. So we have very good result. Here also I have the plastic strain magnitude or the accumulated plastic strain. Also we have values from the 0.3 here in the pyramid. With the using of vibrating barrier, we have smaller, much smaller. It is about by 93%. So here I have the Fourier analysis for the dominated frequencies system structure pyramid with the soil without vibrating barrier and with the vibrating barrier. Without the vibrating barrier, of course, with the consideration of the plasticity behavior. The dominant frequency, it is 8.42 Hertz. But when we have used the vibrating barrier, the frequency, or the dominant frequency, reduced to 0.15 about Hertz. So it is a huge reduction in the fundamental frequency or dominant frequency for whole the system, for pyramid and soil. In the second step, we have
yes. Okay.
now we can hear you.
Okay. At the moment, we still have some time for questions or any questions. If anybody wants to ask a question, just unmute yourself and go ahead.
Yes, hi there.
Hello. Okay, you can go ahead.
I have a question, if possible. Actually, a couple.
Please.
Okay, go ahead.
Go ahead.
Can you hear me?
Yes.
Yes.
Okay, thank you. Can you please go at the very beginning with the model when you show the various frequencies? Yeah, that one. Thank you. So, if I understood, you are saying the first frequency of the pyramid is 0.52 Hertz of the pyramid on its own? Is that is what you mean with that?
0.52.
Really, the first time that I see these results, but I think you know of the paper that is also co-authored by Professor Ayub and Professor Rashid, where we did our linear analysis. Is published. We have different frequencies, actually. I mean, can you explain?
I'm sorry, I noticed that, but I think it is the data. We have different data about the density and the Young's modulus. I received different data, and I noticed the difference between my result and your results. But it is a problem of data about, I think, Young's modulus and density.
Oh, I see. Yeah, I mean, you know, the data has been provided by University of Cairo, so we are all using those data.
I noticed you have used a different density. They send 2,000 kilogram. You have used 2,900 or something like that. So it is different from what I received. Also, I noticed about the Young's modulus, there is difference. I'm sorry, it is a problem of data.
Okay, I mean, so the material of the soil is different from the material of the pyramid for you?
No, it is the same.
And how do you explain then that you have 22 Hertz for the soil and 0.52
geometry?
Hertz?
It is the geometry, and of course the height. Here we have 63 meters. And the geometry, it is different. I have here 35.
I think at our meeting we will discuss more in detail. Honestly, I don't believe it's realistic to have so low frequency, to be fairly honest. But we can discuss more in detail at our meeting. As I said, it's the first time that I see this, so I was a bit surprised about those frequencies, especially if the material is the same. Unlikely you will get so.
Not the same materials, not the same data. This is the problem. So this
between
is
the soil and the pyramid, is the same material or not?
Yes, but the same data you have used in your analysis. I mean, different data used in my analysis.
Yeah, I mean, I'm saying cannot be, but we will discuss at our meeting. No worries. The other things I was asking is, can you please go to the vibrating barrier?
Yeah.
Yeah, this one. So this is the trench of the vibrating barrier. Have you designed the mass vibrating inside this or not?
No, I used it as a block of concrete and with contact.
So practically it's
rigid.
a block of concrete in the soil.
Yeah, and with the interface rigid with the soil.
Okay, I see. I mean, this is not really what we call vibrating barrier. Practically, this is a solid element. Vibrating barrier has an internal unit that vibrates and need to be designed in such a way you reduce the vibration. For what understanding, also the depth is the same depth up to the bedrock. So practically, you interposed a rigid element in the soil. It's good that you had this kind of reduction, but is what I want to say, this is not properly what we call vibrating barrier, because it's just
the results. As I understand from soil structure interaction, it is the effect of the inertial, the structure and the foundation. So here we have kind of foundation, big foundation or big mass in the soil. So we have the same result, but with different technique.
Yeah, no, I understand that. As I said, this is not what we used to call it. For you, I can understand now the model is different, so possibly you cannot use directly until you don't fine tune your models with our because the vibrating barrier with designed have also the internal unit. But yes, I appreciate that. The other question was about the earthquakes. You said that you got the 1992 recorded earthquake.
It's from Egypt. Yeah.
Where do you get that? The recorded 1992 earthquake?
It's recorded in Egypt, and this is the data from Cairo University.
Okay, I think this is synthetic. It's not recorded, this one. I mean, there is also the reference for this, but this is what I was curious to see. So is a synthetic earthquake, not recorded. Regarding also the use of the other earthquakes, you know that other earthquakes are recorded at the surface, but you are applying recorded earthquake at the bedrock. Do you see that this can be an issue or not?
Yeah, there is transfer function. I understand that, but actually in this kind of material, we have damping very small. I would consider it as 0 for this kind of material. So of course, there is a difference between what we have at the bedrock and what we have as recorded, but I used the data received from Cairo University, 12 records. So I used these records.
Okay, thank you. No, well, as I said, I have quite a number of questions because it's the first time that I see these results. But maybe we can talk at our internal meeting for the project.
Okay, of course.
Thank you.
Okay, thank you, Piero, thank you, Mohanad. I think there is a guy called Ahmed Osman. He has a question. He raised his hand. You can unmute and go directly and ask.
Dr. Yusuf Ashraf Osman, not Ahmed Osman.
Ah, Dr. Ashraf Osman. Hello, Dr. Ashraf. How is it going? Okay. Hello, Dr. Ashraf.
How are you? I was the one who asked the question about the vertical component of earthquake in the morning.
Okay, I see.
I see here the analysis in one. Okay, the analysis is mainly here in one direction.
Yeah.
I have a worry. If we apply the barrier in both directions and we apply the earthquake in the two directions, an interaction between those vibrating barriers in both directions or not? My question is, what will happen? Because this is one-dimensional analysis, I think.
I think Piero can reply this.
You mean if?
Yes, if you want, I can reply to this one.
Okay.
Thank you for this. We actually have applied earthquakes for any random angles, but the vibrating barrier need to act, indeed, you are perfectly right from this point of view, in both X and Y direction. So therefore, when you define a random angle, then we divided into two components parallel to the X and Y axis of the pyramid, so parallel to the main sides of the pyramid, and vibas that are in the direction of that component clearly will have a major effect. But they are able to protect from any direction of angle. But you need to have, but you need also to have vibas on the opposite side. This is what, yes, I mean, what has been shown is just one direction, but you need to have vibas that theoretically, but is less effective if the vibrating mass in the trench in one side is able to oscillate in both the direction, one trench is enough. The only problem is that the soil structure interaction in that case is less effective. So it is better to have at least two trenches parallel to two perpendicular sides and to have unidirectional vibas, so to withstand X and Y components of the earthquakes.
So my question is that if we have a trench parallel to the direction of the earthquake, okay, along the direction of the not perpendicular to the earthquake, it's parallel to the earthquake. It has an effect on the, or should be a trench perpendicular to the direction of the earthquake only.
Thank you. The trench can be parallel. The vibrating unit inside need to vibrate in both directions. But if it is parallel, we'll have less effect because the soil structure interaction, structure interaction is less effective when the two trench and the structure are in the same direction of the parallel to the input.
May I interrupt?
That is
May I interrupt?
Sure.
They need to remember that the vibrating barrier is a vibrating mass connected to springs inside this trench. This is the idea. They have to remember this. Okay?
Yeah.
Okay, thanks.
Welcome. I think there is another guy raised his hand. Just unmute and ask direct the question.
Yes, hi there. This is Agi from City University. Piero, well, first of all, I'm looking at the figure in front at the slide that is right now showing, and I see an acceleration that has lower frequencies the first few seconds, and then frequencies become higher, which cannot be true. Anyway, this is something I'm sure Piero will sort out. One question, Piero, is the following, and it's a very one mass with double axis viba. I didn't quite understand the your response, or the ideal, let's say, arrangement of the vibas around a structure.
Mohanad, are you with us?
Yeah, but I think the question for
Piero?
no?
No.
Question for Piero, no?
No question for you.
Yeah.
Or
No.
Piero,
It was for Piero. Piero,
Okay.
are you?
So Piero, can you give us a reply?
Sure. So I was saying, thank you, Agis. It's so nice to also see you here. Regarding as I said, this is the first time I see those slides. I mean, this is not my work. I share with you the concern for the earthquake. This is why I wanted to see us as well. Regarding the VIBA, the test that we have done for various applications, we considered either the solution with a mass vibrating in 3 directions, so practically springs X, Y, and Z, okay? Mainly X and Y, the Z we did for another application, but X and Y mainly. And was able to give, for any direction, a kind of reduction. However, is more effective when the vibrating unit vibrates so in the same direction of the input. Therefore, the trench should be 2 different separate trench, and the mass need to vibrate in a single direction. So a single spring mass system, in my opinion, is, well, from what we have seen, was more effective than we have because we reduce the number of masses. Is more in parallel, because in one case they work in.
Note that, you know, devising a multi-axial dynamic vibration absorber, a VIBA or whatever, is not easy as well. Okay, it's much simpler to have a uniaxial one. One last question: have you ever considered nonlinear soil behavior at all? Under, you know,
for Mohammed?
Well, anyone that, you know, does. It's just a curiosity whether you have considered nonlinear soil behavior under, you know, severe earthquake excitations.
Okay, I think this is really what indeed City University is going to do, or putting nonlinear model. I mean, Professor Ayub.
Yes, this is the analysis for nonlinear
soil. Of the
soil and pyramid.
Yeah.
Soil and pyramid, the same material.
In Brighton, we have done some initial study, but not for this problem, for other cases. And but as I said, really initially, we have not published yet these results. But what we have seen, soil, the VIBA even works better. But as I said, are really preliminary results, so I don't feel so much to disclose, because we have not done a thorough investigation for this. But yeah, so I know that they are doing, that will be part of this project, they will be doing advanced nonlinear soil analysis at sea.
Okay, many thanks.
Thanks to you.
Okay, this is Ashraf Ayub from City University. If I can just quickly comment, I think we had a very nice discussion here, and we can continue the discussion later on. Just about the modeling of the VIBA. This is obviously it's not a properly designed or an optimized solutions that we're doing. We're still obviously waiting for this. This is like a very initial